So, we start a new lecture again. We will start with a new topic in this lecture, which is, so now having studied the structure of various solids, we started metals, then we moved on to ionic solids and covalent materials, which are basically ceramic materials, and then we moved on to non-crystalline materials such as glasses and polymers. So now the question arises is, how do we evaluate their structure experimentally, and how do we distinguish between various materials having same structure or having crystalline structure? So one technique which is very useful and powerful is X-ray diffraction, which is the most fundamental technique to characterize the structure of crystalline materials. So what we will do in this lecture and henceforth in subsequent few lectures is, we will study the basics of X-ray diffraction and its usefulness to characterize the structure of materials. So, all of you are aware of physics of diffraction. So, diffraction, it was initially studied by people like, the effect was observed in 1600s, in 1665 by some Italian scientists, but proper understanding of diffraction came only after Thomas Young conducted his two slit experiments. So Thomas Young conducted his two slit experiment, where he had these two slits and he had a screen here. So these are two slits which are spaced by spacing d, and when the light struck them at certain angle, whatever angle it was, he observed a pattern on the screen which was basically something like that. It was fringe kind of structure. So not very nicely made, but nevertheless you understand what I mean. So he observed a dark and so basically series of, you can say, dark fringes followed by light fringes. So on a photographic film. Okay, so this was a you can say film. The light hit the film, and wherever it had maxima and minima, correspondingly you had bright and dark fringes depending upon the exposure of light with the. So basically so this was started by Thomas Young, who is famous for his two slit experiment, who said that, so you had certain angle of diffraction, let's say, and if the screen, this distance was x, this was L, then and the slit spacing was d, then what he found out was d sin theta was equal to n lambda, and what he said was sin theta was the angle of diffraction, n was the integer. So when n was 1, 2, 3, then he had constructive interference, and when n was equal to half, 3 by 2, so on and so forth, then it was destructive interference. So which means when the angle, the corresponding angle and d, they were the slit spacing and the angles of diffraction, and L lambda was the wavelength. So basically what he said was that there is this condition which needs to be fulfilled for diffraction to occur, where n is an integer. The moment it ceases to be an integer, there is no diffraction, it leads to destructive interference. So basically Thomas Young's experiment laid the foundation of modern diffraction analysis. And basically what it meant was, if you can observe diffraction phenomena using visible light in using two slits, materials, crystalline materials which have atoms which are periodically arranged with spacing being equal to A, let us say lattice parameter, they can be considered as if these are multiple number of slits. So, in Thomas Young's experiment, he conducted the experiment with visible light. The slit dimension was same as that of a light, because you can see from this relation d sin theta is equal to n lambda. Okay. So, since sin theta cannot be beyond plus and minus 1, the d and lambda should be comparable to each other. Okay. So, in his case, the slit spacing was comparable to the wavelength of light. So, the question now in case of materials is that if we consider materials as made up of millions of slits which are regularly spaced in space at a spacing A, this A happens to be of the order of angstrom or so, maybe few angstrom, 2 angstrom, 3 angstrom, 4 angstrom. We need radiation which is of equivalent wavelength. So, it cannot happen. So, you cannot get diffraction effects from metals or materials using visible light. Visible light wavelength is far higher. Visible light lies between 300 to 700 or 800 nanometer, right? Whereas the spacing here that we see in case of materials is of the order of few angstroms, let us say 1 to 5 angstrom. So, the question was, what is that radiation? And this happened only when X-rays were discovered. So, this led to X-rays, which were discovered in 1868 by a German scientist called as Röntgen. He was the one who discovered X-rays first in 1868, and X-rays had the wavelength of the order of lattice spacing. So, for example, copper K alpha X-ray, it has a wavelength of angstrom, which is nearly of the same order of magnitude as you have the lattice spacing. So, this was a major turning point in terms of characterization of crystals post Thomas Young's two slit experiments. So, these are basically, you can consider a crystal akin to multiple regularly spaced slits. So, basically they should also behave like slits, it is just that we need to find a right wavelength which can fulfill the diffraction condition. So, a lot of work was done in 1912, 1900s, early 1900s. So, 1912, von Laue, he discovered X-ray diffraction from crystals. And then in 1912, Lawrence and William Bragg, father and son, they gave rise to Bragg's law. So, that was again a remarkable discovery. These were two landmarks in crystal characterization using X-ray diffraction. So, we will not get into history of it, we will just stop here, but this is basically the message was that you needed to find a radiation whose wavelength was comparable to the lattice spacing, because lattice can be considered as an array of slits, and it happened only when X-rays were discovered, because X-ray had a wavelength which was of the order of which had the same order of magnitude as the lattice spacing. So, where do X-rays lie? Well, let me show you a picture. So, X-rays lie somewhere here. So, you can see this is the electromagnetic spectrum. We have, this is the visible region. Visible region lies between nearly 300 to 700 or 800 nanometers. On the right of visible, which means at higher wavelengths, we have near infrared, far infrared, microwave, radio waves, which are of very long wavelength, and they are not useful as far as X-ray diffraction from crystals is concerned. For diffraction to happen from crystals, you need to have shorter wavelengths. So, UV is nearly 100 nanometer, which is not very useful. So, that is where we bump into X-rays, and these X-rays, the one on the left of the wavelength of the order of 1 angstrom to 2 angstrom are useful for us. You can have X-rays of 1 nanometer wavelength as well, but that is not useful because most materials have lattice parameters which is far smaller than 1 nanometer. So, we need to be in the far extreme of X-rays to have wavelengths which can satisfy our criteria of diffraction. If you further reduce the wavelength, you get into gamma rays, but we do not want gamma rays for diffraction. They are also very dangerous to deal with. X-ray is also dangerous, we need to use them properly, but so this is where we are in this regime of wavelength of the order of 1 angstrom. So, how does X-ray get produced? So, this is a picture which shows you the production of X-rays. So, what happens in this case is you have a heated tungsten filament which is kept at a very high bias, 30 to 40 kilovolt, which is a very large amount of voltage. Under this high voltage, the filament emits electrons, high energy electrons are emitted from the filament, and they leave in an evacuated tube. So, this whole thing is kept inside an evacuated tube, so that you have no scattering, by the air molecules. Okay, so there are no air molecules, and these electrons are focused onto a target, and this target is made up of a material from which you want to generate X-rays. So, if you want to generate copper X-rays, it could be copper target. If you want to generate iron X-rays, it could be iron target. If you want to generate molybdenum X-rays, it could be molybdenum target. And this hits the target, and target generate X-rays at certain angles. Okay, and these X-rays are then taken through windows which are typically made up of beryllium to wherever you want to use them. So, this is how you produce X-ray. Now, since a very large voltage, since the energy of impinging electrons is very high, target gets heated. So, this target has to be consistently cooled with the cooling water, otherwise there is a chance of melting and evaporation. So, this is how you produce X-rays, all right, and X-rays are also used for a lot of other applications such as medical applications, but we will restrict ourselves to the use of diffraction in crystals. So, now, basically how X-rays are generated are, you have these you have these electronic crystals. So, electronic orbitals, you have K shell, okay, and then we have L shell. L shell can have 3 sublevels, okay. So, this is K shell which has corresponding energy Ek, right, and then you have L shells, you can have L1, L2 and L3. So, and then you have, of course, have something called as valence band, and then you have something called as conduction band, you have these energy bands, and then of course you have vacuum level, okay. This is evac, all right. So, this is how energy levels are falling. So, when you have these electrons here, some electrons will be sitting somewhere, okay. So, these electrons are there. Now, when a high energy electron comes in, so this is high energy electron that comes in, Okay. This high energy electron gets knocked off. So, this is incident electron beam. So, this knocks off this electron. So, this electron has been knocked off. Now, what happens is that you have created now a vacant state here. This is vacant state. So, which means something from the top level has to fall to make sure that there are no excited. So, this becomes excited state, right. So, this electron will now come and occupy this place. So, this will the release of this from higher energy. So, this is higher energy electron. This higher energy electron will come and occupy this place, leaving this as empty, and this gives rise to emission of X-rays. So, basically the X-ray energy is this energy, let us say this energy is E1, this energy is Ek. So, X-ray energy will be, so energy of X-ray will be equal to E1 minus, or let us say EL3 in this case, EL3 minus Ek. So, this is how the X-rays are produced. So, depending upon from where the transition has happened, the X-ray will have certain energy. If the electron comes from higher levels, it will have even more higher energy. So, there is a probability of transition. Electron can come from here, it can come from here, it can come from even higher levels, K, L, M, N, you have all sorts of levels there. So, there is a probability of transition, and and there are certain transitions which have higher intensity as compared to other. They may not have same energy, they will have different energies if they are coming from different levels, but the probability of transition from certain levels is higher as compared to others. So, you can say now, you can draw this as K edge, and then we can have L, then we can have M, and then we can have N. So, transition from L to K, this is L, M, N. So, transition from L to K is referred as alpha transition. Transition from M to K is referred as beta transition, and transition from N to K is referred as gamma transition. Similarly, in this case, this will be alpha, this will be beta. Similarly, in this case, it will be alpha. So, transition from the next level to the level below is called as alpha. If you are going to one above, transition from there to the bottom level is called as beta, and so on and so forth. So, this is why we say, when we say K alpha, this becomes K alpha, because the transition has taken place from L to K. K beta will mean transition from M to K. This is K gamma, which is very rare. Similarly, this will be L alpha, this will be L beta. So, these are all X-rays. You will see if you go to your SEM room, you see that chart, right, where different energies are there. You will see for some elements you see K alpha, for some elements you see L alpha, and so on and so forth. These are what those lines are. Basically, transition from if it's L line, it's basically transition from M to L. If it's K line, it's transition from L to K, K alpha. If it's K beta line, it's M to K, and they have different energies, as you can see, because energy is the energy difference between different transitions, different lines is different. Okay. So, now let me show you sample in this. I could just draw it. So, when you now bombard okay. So, and within this alpha also you can have alpha 1, alpha 2, alpha 3. So, because L is made up of 3 sublevels, okay, L1, L2, L3. So from here you can have the transition from the lowest one will be alpha 1, lowest 2 will be alpha 2, and so on and so forth. So you can have these various transitions alpha 1 and alpha 2. Now let me show you the diagram of how X-rays spectrum looks like. So if when the X-rays are produced, on the bottom axis I plot wavelength, on the top axis I plot intensity, y-axis, and as a function of voltage, the X-ray spectrum, because there is a possibility of all sorts of transitions happening, you don't produce just one wavelength, you produce multiple wavelengths. When you produce multiple wavelengths, it's called as continuous radiation, or white radiation. So you tend to produce these lines like that. Okay. So these are lines, and then suddenly at certain you have these. Actually they go more steeply here. Okay, it's far more steep drop. So these are so this is basically as a function of voltage. So this is 10, let's say 15, and this is 20, and this is, let's say, 25 kV. Okay, so this is kV, 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 and you will have 5 somewhere here, let's say 5 kV. Okay, so as your accelerating voltage changes, your spectrum shifts to left, and this limit is called as lambda SWL, short wavelength limit. How do we work this out? We know that EV can be equated to h nu. So corresponding to the voltage, you will have maximum frequency. So lambda SWL is basically C divided by nu max, which is equal to HC divided by EV. Okay, nu max is equal to EV divided by H goes up. So if you work this out, H is 6.6 Planck's constant, 6.6 into 10 to the minus 34 joule per second. C is 3 into 10 to the power 8 meter per second. Electron charge is 1.6 into 10 to the minus 19 coulomb. So lambda SWL works out to 12,400 divided by V in volts. So this is how lambda will, so this is how, so at a given kV, you can see now as the voltage increases, the lambda SWL will decrease. So that is what we see, the lambda SWL decreases as we increase the voltage. And this is also useful because at lower voltages, you get a radiation, but you don't have any characteristic radiation. You have all sorts of wavelengths, you don't know which one to pick from. Suddenly at about 25-30 kV, what happens is that there are some very intense peaks which start developing. These are called as characteristic peaks. Characteristic radiation peaks. So let's say these are these kind of peaks. Okay, these are characteristic radiation peaks. Typically they are referred as, this could be K beta, this could be K alpha. So you can see K alpha is the transition from L to K. K beta is the transition from M to K. So obviously M to K will have higher energy, correspondingly lower wavelength. So K beta will always occur at lower wavelength as compared to K alpha. But intensity of K alpha is far higher as compared to K beta. And that is the reason why we use K alpha radiation in X-ray diffraction, because it's a very intense peak. It gives you high intensity X-rays of wavelength. So this K alpha wavelength is the useful wavelength. Okay. So this gives you a very intense peak. There could be other peaks as well. There could be other minor like L alpha, L beta and all that, but they are not intense as compared to, and they will probably be lower in energy as well, because it's a L would be transition from K, L, M, N, so M to L, right? So M to L transition will be far lower in energy as compared to transition from, let's say, from M to K. So it works out. So this is all dependent upon probability of transition and what is the yeah. So a lot of factors it is determined by, but nevertheless what we get is K alpha radiation with very high intensity corresponding to a wavelength which is useful in nature. And these plots are called as continuous radiation because they are basically continuous contours. So they give you the overall what you get out of a material at a given voltage. So they have all sorts of X-rays, and the intensity changes of course as a function of wavelength, but there is no very sharp peak at lower voltages. It is only at high voltages you start getting these sharp peaks, because you are then able to excite the electrons from K alpha. Remember, if you want to excite the electron from K alpha, you also need higher energy, because K alpha is the bottommost shell. When you bombard material with at higher at lower voltages, you are only exciting electrons from the top orbitals, because they are loosely bound as compared to the one inside the one which are close to the nucleus. Okay, so this is what the X-ray spectrum looks like, and if you, for example, look for various materials, so various materials which are used are copper, molybdenum, iron, to give you this X-ray spectra. So we use copper K alpha, we use moly K alpha, Fe K alpha, chromium K alpha, and so on and so forth. These radiations are used, and they will have different wavelengths.
Criteria for the material to be a target material.
Most of these are metals because they emit X-rays which are useful to you. So you can, the radiation that you use depends upon type of materials that you want to examine. Okay, so for example, copper gives you a wavelength which is useful in most circumstances, but copper wavelength is not very useful in case of iron containing materials. That is where you choose chromium target. So the criteria, and I'll come to that in a little while. So probably we don't have enough time today. We'll probably wind up here. So what we have seen basically is how X-rays are generated. What do you mean by K alpha and K beta and so on and so forth. In the next lecture we will see some of these intricacies as to which X-rays to choose, which is dependent upon the absorption of X-rays by the material. What is, because X-rays also create radiation out of materials. So whether it leads to any fluorescence or not. So we'll discuss that in the next lecture.